Hey, let's begin with the P series test. So up till previous lecture, we got familiarized with the geometric series. We also know about the arithmetic series from our school time. And we also know that reverse of the arithmetic series is called as the harmonic series. And in this lecture, we're going to discuss about some similar series known as the hyperharmonic series, which is summation of 1 upon n raised to power p, where n goes from 1 to infinite. P may be any real number. So, what is P? So, if P equals to 1, then we will get 1 plus 1 by 2 plus 1 by 3 up to so on, which is we know that it's a harmonic series. So, if P equals to 1, we will get hyperharmonic series is simple, just harmonic series, which we have discussed already familiar about from our school time. And also we will find that how P changes, and we will discuss about in this lecture the property of P. It will be converges if P is greater than 1, and it will diverges and if P is less than or equals to 1. We will discuss about its proof and also discuss about its examples and so on.
Let's start with P series test. So, P series test is also known as hyperharmonic series. So, the series by which 1 upon n raised to power p, we do summation from 1 n equals to 1 to infinite, then we will get our P series. So, if we do summation of 1 upon n whole raised to power p, where p can anything else and n will be vary from 1 to infinite. So then we have to determine whether we get our series as convergent or divergent or an oscillatory series. So there are some methods for doing this. We will also drive these. So here are the values of p by which it converges and diverges. So if it is greater than 1, it will converges, and if it is less than or equals to 1, it will diverges. So this series will diverges. Now let's see why this is called as a hyperharmonic series. We already discussed about the geometric series in the previous lectures, and it is just a harmonic series. And we know that harmonic series is the opposite of arithmetic series, and we add by just taking opposite of any arithmetic series, and we just add it. So but hyperharmonic series is not like that. It may be 1 upon n raised to power p. If it is p equals to 1, then we may say that it is a harmonic series. But otherwise, we determine each and every value for p for calculating our particular series, and it is that's why called as the p series. So it is a high harmonic series, but the value of p determines whether it is converges or diverges or not. So that's why it has a variety of values for p. It may be anything else, any real number, any integer, and any real number maybe. So any rational number. So it will be, that's why it's called as hyperharmonic series. Now let's discuss about its proof. So case 1, when is greater than 1. So we have 1 upon 1 upon p raised to power p always we for any value of p it will equals to 1. Now let's see, when we go further in a series 1 upon 2 raised to power p plus 1 upon 3 raised to power p. So we know that 1 upon 3 raised to power p is always less than 1 upon 2 raised to power p. So this is the condition we have applied here. So 1 upon 3 is upon p is always less than 1 upon 2 raised to power p, and we will get that 1 upon 2 raised to power p plus 1 upon 2 raised to power p should be equals to 2 raised to power 2p. So as we know, when we add both these quantities, as this 1 upon 3 raised to power p is less than this 1 upon 2 raised to power p. So when we add, we will always get less than this particular right side equation. So when we add them, we will get 1 upon 2 raised to power p minus 1. Now let's go further more in order to uh, find any property of the series so that we will get something else. And as we do further, we will get that 1 upon 4 raised to power p up to 1 upon 7 raised to power p is always less than, as we know, as usual. This is the reason behind is because 1 upon 5 raised to power p is always less than 1 upon 4 raised to power p. So we get a maximum value of any series which is in the right side such that it cannot exceed 1 upon 5 raised to power p plus 1 upon 6 raised to power p plus 1 upon 7 raised to power p should always be less than 1 upon 4 raised to power p plus 1 upon 4 raised to power p plus 1 upon 4 raised to power p. And 1 upon 4 raised to power p, which is fourth one which is used, is cancel out with the left one. So this is the uh, reason why we use this inequality. So when we solve this right hand side equation, we will get that 4 upon 4 raised to power p equals to 1 upon 4 raised to power p, which is 1 upon 2 raised to power p of whole square. So that's how we will get this. So as we go so on, we will do that for the next 8 terms. So as we do that thing, we'll find some kind of property of the series, some kind of uh, common term should be repeated. So as we will notice that 1 upon 2 raised to power p minus 1 is our common ratio, and we will just making our p series to confine it as a geometric series further. So when we solve it and we split terms into such that they will be defined into any geometric series in such a way that we will get 1 upon 2 raised to power p minus 1 as our common ratio. So as we do further, we will find that 1 upon 2 raised to power p minus 1 is always less than 1, because for any value of p greater than 1, we choose in this case p is greater than 1. So we when p is greater than 1, then 1, we know that denominator 1 upon 2 raised to power p should always be greater than, when p is greater than 1, 1 upon 2 raised to power p minus 1, denominator is 2 raised to power p minus 1 will always be greater than 1. So overall 1 upon the greater denominator than 1, which is 2 raised to power p minus 1, for every value of p greater than 1 will always gives us a bigger value than 1. So we will get denominator bigger from numerator. So we will get always value of this particular common ratio should be less than 1. Now, as common ratio is less than 1 in geometric series, so above series is convergent, as we have discussed in the previous lectures. So geometric series, I hope you have already done with this. So now let's begin with the case 2. When p is 1, as summation of 1 upon n raised to power p equals to 1 upon n. So we know that when p is 1, so we will get that 1 plus 1 by 2. This, we know that this is when p is equals to 1, this is called as a harmonic series. We all know that. So 1 plus 1 upon 2 plus 1 upon 3 plus 1 upon 4. So this is just opposite of uh, arithmetic series, which is known as harmonic series. So when we do that, we will split our series into 1 plus 1 by 2, which we will get 1 plus 1 by 2 by any, we can't change anything else, because 1 we can't change, because we have to relate it with the right hand side, which is also 1 by 2. So let's do with this second term, second split term. So second split, we are going to use it. 1 plus 3 plus 1 by 4 is always greater than 1, because we know that 1 by 4 is always less than 1 by 3. So that's why we will get this 1 by 3 plus 1 by 4 is always greater than 1 by 4 plus 1 by 4, which is equal to 2 by 4, which is 1 by 2. So as we go along, we will say that 1 upon 5 plus 1 upon 6 plus 1 upon 7 plus 1 by 8 is always greater than the last term, that is 1 by 8. 1 by 8 plus 1 by 8 plus 1 by 8. Because this last term is the smallest term. So we use to sum up these things in order to get the minimum of the particular sum, so that it always, because other terms are greater than this. So when we add this last term 1 by 8 multiple times 4 times, as number of the uh, terms in this whole left hand side, we will get that it must be always greater, because all the left terms uh, first before the 1 by 8 is always greater than it. So when we take this 1 by 8 as many times as the previous terms, we will get that it is equals to, it is always greater than 1 by 8 plus 1 by 8 plus 1 by 8 plus 1 by 8. So these three terms should be greater than 1 by 8 plus 1 by 8 plus 1 by 8. So sum of them should also be equals to them. So that's why we use this particular intuition. So in order to relate with it, so we will now get equals to, right hand side equals to 4 by 8 equals to 1 by 2, and so on. We will do this for the other terms too. Then we will find that in the last, now terms in the series is greater than 1 by 2, and the series cannot be less than 1 by 2. So we know that the terms is greater than 1 by 2, and the series cannot be less than 1 by 2, because, so here are now if we add 1 by 2 very much time, as many times we have, so we will must get an infinite, from infinite terms we will get infinite sum. So this is something called as the definition of the divergent series, as we have already discussed in our previous lectures about divergence of this series. So this is geometric series with a equals to half. So when a is equals to half and r equals to 1, so that's how we will get. So it is a divergent series. So it must be divergent. So as we go along, n is to power infinite 1 plus 1 by 2 plus 1 by 2 up to so on, it must be diverges to infinite. So of series 1 by 1 upon n of the harmonic series. So harmonic series always divergent, it never converges. This is also the fact. So now when p is less than 1 and n raised to power p is less than n, now we know that if p is less than 1, then n raised to power p should also be less than n. Now 1 upon n raised to power p should all will be greater than 1 upon n. So by using our uh, inequality rules, we will get this for all values of n. Okay, but the series 1 upon n is divergent. Now if this is divergent, we know that divergent means it approaches to infinite. So the greater the, because for any value of n, we have 1 upon n raised to power p is greater than 1 upon n. So if 1 upon n go from n equals to 1 up to infinite and it diverges, then 1 upon n raised to power p, which is greater than, each term of this series is greater than when go from n equals to 1 to infinite. So hence, so this also be divergent. So this is the fact how we prove it using our previous case question. So previous case of the p series test. Now let's look at some examples. First is n raised to power cube whole square upon n square whole cube root. So we will get that n raised to power 3 by 2 upon n raised to power 2 by 3, and we just minus our power of denominator from numerator power, 3 by 2 minus 2 by 3, which is by taking LCM we will get the 2 into 3 and 3 square minus 2 square, which is 9 minus 4 upon 2 into 3, which is 5 by 6. So here n is 5 by 6, which is less than 1. So the given series is convergent series. Now in the second question we have n cube upon n square by 3, which is n cube minus 3 by 2, and we will get that now n is to power 6 minus 3 upon 2, which is n is to power n cube upon 2. So that's how we will get. So p is, if p is here, p is actually 3 by 2, so which is greater than 1, the given series is divergent. So in the last case, n square upon n whole under root n, which is n square minus, so it we will get that n is to power 4 minus 1 upon 2, which is n is to power 3 by 2. So this is also a divergent series. So hence we relate our formula for p series test in order to compute our whether to check one of any kind of series which included the power of n, we may get that it is a divergent or convergent series by using our p series test. So that's how today's
I
lecture.
hope you enjoy my content, and please don't forget to like, subscribe to my channel. Till then, keep learning and keep exploring. And as always, feel to email me at dsvfx6789@gmail.com.